So we're recording now. This is our RISC-V review session. And so let's get started. Let me share my screen. Okay, share that one. Okay, so for the people on Zoom, can you see my screen? Can you see the slides? Yeah? Cool. Chat. Okay, so people can see the slides. And let's get started. I'm gonna close this for now. Okay, so before we get started, just another reminder, if you're online, if you're on Zoom, please try not to post questions in the chat. It's really hard to keep track of, and there's like a lot of like moving parts here, so I'm not, it's kind of hard to keep track of questions. So please post it on Ed, right? And if you're in person, you can just raise your hand, okay? Okay, so let's just jump straight into a review for RISC-V, right? So how many people are like familiar with RISC-V? How many would say that they're very, very good at RISC-V? How many say they're like decent at RISC-V, but still need a bit of help? Okay, and if you need a lot of help with RISC-V? Okay, sure. So this is just a general pointer of thinking before you solve a problem on the midterm, right? Because I always get into like, whenever I take exams, I like get into like a panic. There's like a time crunch. There's so many questions to do. And sometimes we forget to just think before solving our question, right? And this applies to anything, whether it be exam problems, whether it be like life problems, whether when you're coding. So you should think about these things, right? So first thing you should think about is, what is the goal or expected behavior? So let's say you have some problem on the exam, and it asks you to write code. Before writing any code, think about what the goal of the function is, right? Once you do that, identify what values are important, what variables are important, right? So if we're like iterating through an array, maybe you want to have some like variable that has a counter that goes through the array, right? Some index variable. And then you also need variables that store the arrays that you have, right? So think about what variables are important. And then you should identify any repeated patterns. So for the case of iterating through an array, there's a repeated pattern of shifting the index one by one, right? And then once you identify all of that, figure out the logic of your program. Think of it through in your head. Think it through in your head before you write code or handwrite it on the exam, right? Does it work? Just do like sample cases. Do like a small base case. Does it work? Do the case just above the base case. Does it still work? Right? So remember to like think before you problem solve. Right? Okay. So let's get right into it. This is our toy example in C. We have this code that basically just loops and does work inside our loop, right? So do work is just a black box function. It can be anything. It's just like an abstraction for us, right? Inside our loop, we're doing work. And this is a really common programming pattern. You set some variables, right? You loop while some condition is true. You do some work within your loop. And then at the end of the loop, you change some variable values. And ideally, that would get closer to your ending condition, right? And then you repeat. So in this case, we have S0, and we set it to be 0. And while it's less than 4, you want to do some work, right? And then you do the work, and then you increment S0. So now S0 is 1. And then the next iteration, S0 will be 2, and then 3, and then 4, and then you hit 4, and you say, okay, 4 is not less than 4. Now we're done. We're done with our loop, right? So this is just our toy example. Okay, so my first little quiz question for you, and imagine that I'm not here like explaining it. Just think about this as like, you see this on the exam. I want you to translate this C code to RISC-V. How would you do that? And I'll give you just like a couple minutes, maybe 3 to 5 minutes to think about this, and then we'll talk about it. Okay. Okay, so hopefully everybody got a chance to take a look. Can anybody give me a hint? Like, what's the first thing we should do in our RISC-V code? Any ideas? Yeah, Khalid? Sure. Okay. Yeah. So the first thing we can do is basically just initialize S0, right? And then what's our next step? What's the next thing we had to write? Someone other than Khalid. And if you're on Zoom, you can feel free to unmute and then answer. Yeah. Yeah. So basically, like, you start your loop. Is that what you're saying? And initialize S0. Yeah. So yeah, you start your loop, and we initialized S0 to be 0, and we need to like have some value 4. So if we get to 4, then we break, right? So yeah, you loop and you break if S0 is greater than or equal to 4, right? And then you do your work within the code. And then what's the final step, the key step? Yeah. Yeah, exactly. So if we don't do this step, we'll just get stuck in an infinite loop because we're not getting any closer to our break condition, right? So yeah, increment S0, that's correct. And then you just repeat your loop. So how does this look in RISC-V? This is how it looks. We set S0 to be some value, which for in this case, it's 0. And we start our loop, our while loop, right? So we have a label. And in general, in RISC-V, whenever you want to jump to a certain point of code, you should put a label there, right? So we're putting a label, our while loop, and we'll go through our loop. And once the end of the loop is hit, okay. Okay, so let's just continue. Once the end of our loop is hit, we'll jump back to the top of the while loop. And every time we jump back to the top, we're checking if we want to break, right? So while we load our immediate into T0, and T0 just holds the value 4, right? Then if S0, right? If S0 is equal to T0, then we break to our done condition, right? If S0 is greater than or equal to T0. So there's one main difference to note here. In our C code, we have while S0 is less than 4, right? So in C, the condition that you put into the while loop is like, while this is true, you continue, right? In RISC-V, it's sort of the opposite. In RISC-V, you enter your while, and then you say, if this is not true, then get out of here, right? So instead of having S0 less than 4, you just say, is S0 greater than or equal to 4, right? So that's the break greater than or equal, BGE. That's what that means, right? And then you jump and link to do your work. We'll cover jump and link, these jumping instructions. But basically, jump and link do work is calling the function, the do work function. And then we increment S0, and we jump back to our while label, right? So this is our translation from C to RISC-V, okay? Okay, so let's talk about jumps. And I know a lot of students have trouble thinking about jumps. It is really, really confusing sometimes. There's like J, there's jump and link register, jump register, right? There's so many different things, so it's kind of hard to like keep track of all the different jumps, right? So here's our main idea. We want to jump somewhere else and potentially remember your way back, right? This is linking your way back, right? So jump somewhere and link. So let's think about what these RISC-V instructions do, right? What would this instruction be doing? Yeah.
Jump to label, then go back to the return address.
Yeah. And can you explain like what a return address is?
No, but I want to say it's connected to the coding practice.
Yeah, exactly. So yeah, you're completely right. You jump to the label that's provided. And before we jump, I like to think of it as like remembering where you were before you jumped, right? So that's your like program counter. PC stores where you are in the program. And within our return address, we will, before we store this, before we jump to the label, we want to store our return address, right? So the return address tells us where do we jump back to after we jump to the label, right? So yeah, that's completely right. Store our PC in the RA register, and then we jump to the label. Can anyone describe what this instruction is doing? Also remember, if you're on Zoom, feel free to just unmute and answer. Yeah.
So what it does is that it sets the program counter at line to the line not labeled, the address of the line not labeled, and it also adds for contact the row. The register the row. It's just dominating label and not storing.
Yeah, exactly. So completely right. The main idea is that we're trying to store this return address, but x0, the x0 register, is just reserved for the 0 value. It can only hold 0. So we attempt to store the program counter where we want to return back to into x0, and then we jump to our label. So in effect, this is just like forgetting the way back, right? It doesn't link our return address. Okay. So any ideas what this does? JLabel. Yeah, exactly. So yeah, JLabel is just a shortcut for jump and link x0 label. So it forgets the way back, does not store the return address, right? So as an example, see the JLabel. We use this inside our example before, right? We use this inside this example. At the bottom there, it says jump while. We just jump back to the top of the loop, and we don't need to store the return address because eventually it'll come back down there anyway, right? So good answer. Okay. Now let's think about these instructions. What would this instruction do? So JAL-R stands for jump and link register. Yeah, Khalid.
So instead of jumping to a label now, basically what it does is it takes the RD of the register. That's going to hold some memory address that you have to go to.
Exactly.
It's going to convert the offset to type of instruction to multiply by 4. Add it to the RD. Put that in the program counter and then do the same thing as before. Like the RA is going to hold the return address that you want to go back.
Yeah. So yeah, that's exactly right. RD stores our basically it's an address. So it's a pointer to some other location in code, right? So we would jump to that address and add some offset to that, right? So you jump there and add the offset. And just like with JAL, with jump and link, we're storing RA, right? So store our program counter in RA, and then you jump to the address RD plus offset. Okay. And this is very similar to jump and link. Instead of a label, it takes a register and an offset. Right? Okay. Any idea what this would do? Jump and link x0 RD0. Yeah, go ahead.
I think that it does the same thing. So it just jumps to the line that
Yeah, exactly. So we're jumping to the address RD, like you said, and with no offset, we're not jumping above or below. The offset is 0, and we're trying to store the program counter into x0, right? But we can't do that because it only holds 0. This forgets the way back. And JR stands for jump register. It's just a shortcut for the above. It'll jump to the register and then forget the way back, basically. Yeah, so it's a shortcut. Okay. So yeah, usually we pass in the register that we want to store the return address in. But let's say we leave it out and we just do jump and link label. So we'll jump to the label, and implicitly JAL label will store the return address inside x1, which is called RA. Right? X1 is RA, and it's made for return addresses. Right? So JAL label will implicitly modify RA, and same with JAL-R RD0. Right? They'll implicitly store RA or modify RA. Okay, so let's look at some common uses for jumps. Using J and then a loop name it'll just jump back to the loop header, right? So you initialize some loop with a label. You say, okay, this is our loop. Then we do all those steps that were in our toy example. And then at the end, we jump back to the top, right? So it'll keep repeating until some condition is hit, okay? Jump in link function name. So this is a common way to call a function, right? So it'll jump to that label, that function label, and then the return address will be stored in RA, right? If you want to return, you use RA. Okay, and then this is used, jump to register RA is often used at the end of a function, right? So let's say you called JAL function name, you jumped into a function. At the end of the function, you can call jump register RA because RA stores where you want to go back to, right? So you just jump to that register. And return RET for return does the same thing, right? Yep, usually used at the end of function. Okay, so now let's go into calling convention, which is also very, very confusing. Yeah, after taking this class in the spring, one thing I realized is that RISC is just confusing and it's really hard. So hopefully this review session will like clear some things up, right? So the first thing that I was just like, I didn't even like think about it was caller versus callee, right? What is a caller? What is a caller? A caller is the program that calls the function, right? So a caller calls the function. And then what is a callee? A callee is a function that's being called by some other program, right? So generally the caller will be using like JAL to jump to a function, right? And the callee will be like jumping back using return or jump register RA, right? Okay, so from the caller point of view, if you're a caller, you are calling a function with JAL, right? Usually JAL. You can use JAL R if the function address is stored in a pointer, right? So, but usually the common use is JAL, okay? Before calling your function, you need to understand what arguments the function takes in, right? Can anyone tell me where we load, what registers we load the arguments into? Yeah? Exactly, yeah. So you load into the A registers and each function will have its own like function signature, right? And it tells you which A registers you find your arguments in, right? So you load them into the A registers, and after calling your function, you need to understand what the function returns, and you'll find these return values in A0 and A1, right? A0 and A1. Okay. So hopefully everybody is writing it down. After calling the function, only the S register values and your stack pointer will stay the same. Only those values will stay the same, right? One way I remember is S for saved, right? The function will take care of those S registers, right? So if you're in your function, you have some values in your S registers, and then you jump to some function, right? After the function is done calling, your S registers will have the original values, right? But you have to assume that all the other register values are modified. This means your T registers, your A registers, and your return address, right? You have to assume that it's modified. And why is this? This is just calling convention, right? It was just decided, it's like arbitrary. You save the S registers, T registers, A registers, RA, function doesn't have to take care of it. Okay. So calling convention for the callee, right? If you're the callee, you're the function being called by a program, right? And this program can be another function, right? Okay. So first step, you can find your argument values inside your A registers, right? Why? Because the caller put in their arguments into the A registers. So now once they call you as a function, you know you can find in the A registers, right? And also RA usually will hold the place to return to in your program, our return address, right? So if you want to return from the function, just use RA. What registers do you use? That's something else you have to think about. If you're using S registers, you have to remember the original value, right? Because it's your responsibility as the function being called to store these S register values, right? So make sure you don't modify S registers before saving them. Now, where can you save these S registers? Any ideas? Yeah, Khalid? Yeah, you store it onto the stack. So the way you do this, remember the stack grows from top down, right? So growing down decreases your memory address. So you decrement SP, which is your stack pointer, and then you want to use store instructions, store word and store byte, right? Okay, and let's say your function calls another function, right? What does this mean? Whenever you call a function, you are modifying RA, right? So imagine this, there's a caller and it calls you, the callee, right? And you're remembering the return address to the caller, right? That's stored in RA. But if you as the function call another function, you will overwrite RA in the process of calling that function, right? If the function calls another function, the original return address will be modified, right? So if you're calling another function, you need to make sure to store the original return address, right? So things you might want to store: S registers and return address. Okay. Oh, wow, that's bugging. Okay, so here's our toy example. Fix this function, right? Our function is called myFun, or I guess that stands for function. My function, right? We load some immediate into T0, and then we call this like black box function. Black box takes no arguments, and the return value is in A0, right? And then we want to add 1 to the result of black box, and then return. So I'll give you guys like maybe 5 minutes to fix this function, right? And consider the calling convention. Make sure to consider that. Okay, so hopefully you guys got a chance to fix this function. Just off the top of your head, what seems to be an issue with this function? Some possible issue. Yeah. So what he said was we're using the value t0, we're loading 1 into it. And after we call black box, based on calling convention, we can't assume that t0 will stay the same, right? We can't assume that it'll still have the value 1. So what would you do to fix that issue? Any ideas? Yeah, Khalid. Yeah, exactly. So basically, we can save it onto the stack, right? So let's walk through it. Oh. Okay, yeah, let's walk through it. So, okay, before I walk through it, is there any other issue? There's one more issue other than t0. Yeah. Yeah, exactly. So for the people on Zoom, the student said that RA will be modified when we call jump and link black box, right? Whenever we call a function with jump and link, it will modify the return address, right? So 2 issues. We need to save RA and we need to save t0, right? So how do we do that? At the beginning of our function, let's just store RA, right? So we decrement our stack pointer, right, to have space for 4 bytes. That's why it's -4, right? Because the address is 4 bytes in memory, right? So you decrement the stack pointer by 4, and then we can do store word, right? And the reason it's 0, so 0 is the offset, right? So we have a stack pointer, and we have 4 bytes empty above it right now after we call this add I to the stack pointer. And we don't need to have any offset because it will store from that point in memory growing up, right? So that's why it's 0, right? The offset is 0. So now we have RA stored, right? So now we can continue as normal. And we want to protect t0 from our black box function, right? So we're storing it onto the stack like Khalid said, right? So we just decrement our stack pointer again, store word, right? t0 is an integer and integers are 4 bytes or 1 word. And we store that onto our stack, right? So now our stack has the return address and below it, t0. Now we can call black box where jump and link modifies t0 and RA and load back t0 afterwards, right? So now we have our value back in our register t0 and we increment the stack pointer, right? Anything below the stack pointer will just be like garbage, okay? And then just like normal, we add 1 to our result. And then before we return, we want to load back our return address, right? That was the entire point of like saving RA so that we can figure out our way back, right? And then you return. So this is our fixed function. Question? Do you need to put? Okay, good question. So you're asking, do we need to put anything on that line, jump and link black box? Do we need to put any like register in between, right? Okay, good question. So jump and link does take a register and a label, but if you leave out this register, then it'll implied modify register RA. It'll modify register X1. So yeah, if you wanted to, you could write in like jump and link RA black box, and this would have the same effect, right? Yeah. Good question. Okay, so hopefully everybody took note. Oh, question? Yeah. Oh, okay. Okay. So yeah, so the question was, why can't we just store RA and T0 all in one step, right? So we're storing RA in the green section and we're storing T0 in the red section. Why can't we just squish them all together, decrement this stack pointer by 8, and then store both our values, right? So the issue is, if we do that at the beginning of the function, we store T0, we haven't set a value for T0 yet, right? Question?
Yeah, so I'm saying like after the
Uh-huh.
there's like li T0, comma 1, then add I.
Oh, okay. Okay. Yeah, that would work also. Yeah, that should work.
That like violates calling convention because we're like switching the like the big function calling convention with the call calling the inner function. I guess it's not like violating.
Calling convention?
Yeah, because the RA is in reality my function is RA, right? And then if we turn out after that, we're squishing two parts together. You know, like the red part is for the inner function,
Right.
and then the green part is for my function itself for the outer function that calls my function.
Uh-huh.
Right?
Yeah.
So if we switch the two colors together, is that like a violation?
Let me take a look. I mean, the entire gist of calling convention is you have to save the S registers. Or even saving RA is not even part of calling convention. It's just so we have a way back, because we had to store RA for our program to function with expected behavior, right? So storing the S registers is calling convention. And calling convention is also whenever you call a function, everything other than the S registers and SP is destroyed, right? So I don't think it would violate calling convention. You're saying if we took the green part and moved it down to the red part?
Yeah. So it doesn't matter where you store it, as long as you store the value somewhere.
Yeah. As long as it's stored, it doesn't violate calling convention. But I will say, like, general good practice is to have a prologue before your main function body, and then an epilogue at the end. That's just like a general pattern you should use. But I guess as long as it's stored, it doesn't violate calling convention. Question?
I guess that one disadvantage of considering the green section along with the
Mhm.
and that storing all of the variables after assigning to 0 would be that if we did have a function with more than one of down, then we have to store and load the order.
Right.
Whereas if we only do that at the start of the function and at the end, then we don't
Yeah, exactly. So basically what was said for the people on Zoom, one downside of storing RA every time we have gel is that we're like storing and loading repeatedly for no reason, right? When we could just like at the beginning of the function, store RA and then retrieve it back at the end. So in this case where there's only one gel call, it's fine. But if you had multiple function calls within your function, then you would be like storing RA and retrieving RA repeatedly, like doing extra work, right? Yeah, good point. That was a good point. And also a good question. Okay, so let's continue. Let's get into a exam level problem, okay? This is from summer 2019 and midterm 1, question 5. Or actually, before we start this problem, can I get a show of hands? How many of you like want to take like a quick break? Like a 5-minute break. Khalid? Okay, wow. Okay, I'm impressed. So I guess we'll skip the break. Sorry, Khalid. I also wanted a break, low-key, but okay. So let's just continue, right? Let's look at this question. We're implementing string copy, right? String copy. And what it does is it takes two arrays, right? Two character pointer arguments. And remember that arrays are also represented as pointers, right? Like if you're representing an array, you represent it as a pointer to the first element, right? So that's why our two arrays, source and destination, are represented as a character pointer, right? We're pointing to the first element in our array, which is a character, right? And it also takes some integer n, right? Some integer n. And what it will do is it will copy the first n elements from our source array into our destination array, right? But if it reaches a null terminator, right? So once you hit a null terminator, it's basically like the string is finished, right? A null terminator denotes the end of a string in C. And in C, strings are character arrays, right? So you'll have, let's say I wanted to represent the string hello. I would have a character array that stores H, E, L, L, O, and then the null terminator, right? Just the 0 value, okay? So what string copy does, it'll copy the first n elements, or if it hits a null terminator before then, it will just stop there, right? Okay, so yeah, and it returns a pointer to destination, okay? So let's just take a look at this pseudocode. This is like Python-ish pseudocode. And let's first convince ourselves that this code works, right? So our pseudocode, we take in a source array and a destination array and some value n. And then we want for n values, we'll copy the source character into destination, source into destination, source to destination until we hit n, right? Or until we hit the null terminator. So let's have a counter variable I, and in this case, I is equal to 0, right? And while I is not equal to n, we will copy one character from our source to our destination. And then at the end, we'll increment our source pointer, right? So let's take a look at this example. Let's say we start running execution on this code, right? N equals 3, and source is some array. It's just a random array. And destination, there might be some values there, but they're not important. So NA, right? So I equals 0, and we copy a character and then increment I. Copy a character, increment I, right? Until I hits n. So now after this step, we copy the character, I is at 1. Copy a character, oh. Okay, copy the character, I is at 2, right? And now we copy the character. Whoa, okay, these slides are being weird. Okay, so we copy a character and now I is 3, right? So now our function is done and we just return this destination pointer, right? See the red destination over there? That's actually a pointer to the value 2, basically. So yeah, we return a character pointer. Okay, so this is an exam level problem, so I'll give you some more time. Write the RISC-V code that will perform string copy, right? And I'll give you the pseudocode on the left. So translate this to RISC-V code. And I'll give you 10, 15 minutes because this is a pretty challenging problem, okay? Yeah, right now the time is 3. So maybe around 3:10, we'll discuss the solution.
well connected.
Let me
You're muted. Hi, you're muted, so we cannot hear you.
Okay, cool. Okay, for the people on Zoom, sorry, I didn't realize I was muted. But basically what I said was we're going over our RISC-V code for stir copy, right? And we can find our arguments inside our A registers, right? Based on calling convention. So A0 holds our pointer to our destination array. A1 is a pointer to our source array. And A2 is a pointer for n. Okay, yeah. Okay, so we're loading our counter to be 0, and we're storing our pointer to destination, right? And now we enter our loop. So first we load the character from our source array using load byte, because remember, characters are 1 byte, right? Characters are 1 byte. So we load a byte that's reading the character, and that character is stored in T1. And then we store this character into A0, our destination array, right? And then if our source is the null terminator, then we can just return, right? So if T1, which is our character, is equal to 0, then we just end. And we'll have an end label at the very, very bottom, right? Okay, so now we add 1 to our counter, and we add 1 to our source pointer and our destination pointer, right? So that's how we're going through the array. And T0 keeps track of how many values do we have to process that are left, right? Okay, and then we repeat the loop. And then at the end, we just move. Remember, at the end of a function, you have to load your return value into your A register, right? A0. So we're moving our destination array into A0. And that is the solution. This is the iterative solution for stir copy, stir and copy. Question? So the question was, is it okay to use load word and save word instead of load byte and save a store byte? Okay. Can anyone find any potential problems with that? Yeah. Yeah, yeah. So yeah, basically, we know that the elements that we're processing are characters, right? And a character is just 1 byte. So if we want to process our characters byte by byte, right, we would use load byte and store byte. Because if you use load word, let's say in this example, you use load word, that would actually load in the value of 4 bytes, 4 characters, right? Because a word is 4 bytes. So if you use load word, it loads 4 bytes, and each character is 1 byte, right? So it'll load 4 characters. Oh yeah, yeah. So in the case that your array had integers, then you would use load word and store word, right? Because the integer is 4 bytes. So yeah, make sure you're like careful about which elements and what size they are, right, in your array. Because your code will change based on the elements you're processing, right? Good question. Another question?
Can I ask over the Zoom?
So the question was, is there any situation where we use the half load and store? Because there's load word for integers and load byte for characters. Is there a situation for load half? And half is 2 bytes. Is there a situation for that? I mean, it all depends on like what purposes you're using your code, your like program for. So I can imagine some scenario where someone doesn't want to store like, doesn't need the full range of an integer and they just want to store half, right? So instead of a 32-bit integer, they treat it as a 16-bit integer because that's all they need. So I can imagine a scenario like that. I think I'll get back to you at the end of the session. That was a good question. Question?
What if we don't change that just like use A0 offset to or something? Do you have to like assign A0 back to A0 or
so you're saying what if we don't modify A0 and we just use like some offset to keep track of where we are? Yeah, that would work. So in this case, we're modifying A0, but in a case where we're using some index and offset, yeah, as long as you're loading and storing the right byte, that would work. No, you wouldn't have to, because A0 would already hold the value that you intend to return, right? So if it already holds it, then you don't have to do that, right? Okay, question? It depends on how you wrote your function. If like, so within this function, A0 is being modified and we keep adding 1 to it to get to the next value, right? So at the end of our function's runtime, A0 won't be the original like pointer to the destination array, right? It would be somewhere over to the right. And that's why at the beginning, we stored the original A0 inside T2. So we hold on to the original pointer, right? But if you had some code where you leave A0 as it is, and you just like calculate some offset at each time and use that, then at the end, A0 still has the original pointer to the start of destination, right? So in that case, you wouldn't have to move or change A0 at all because it has what you want to return, right? Okay, good question. All right, so let's move on in the interest of time. It is 3:20, so we have 10 minutes. So let's just take a look at this recursive solution, okay? It's the same idea, except recursively, okay? And this is the pseudocode on the right, right? So our base case, if n is equal to 0, then we're not copying anything. So we just return our destination array, right? Like stir n copy, the main point is to copy n elements. And if n is 0, then we're copying no elements. So we just don't copy anything and we return our destination array, right? If not, then we copy one element, right? Check that it's not a null terminator. And if it's not, then you call your function on that sub problem, right? So you would do source +1, dest +1, and instead of pointing to 2, in that case, you would get this smaller array that starts at the value 9, right? So if n is equal 0, you just return the destination array. Well, let's say n is equal to 1, right? Then you would have to copy the element, and then you just recurse. How many people here took 61A? Okay, yeah, this is like a huge thing in 61A. like a recursive leap of faith, like over and over again. That was basically the entire class, I feel like, right? So much recursion. But yeah, we're using it. It's applicable to 61C. Recursing with a leap of faith, right? So now our sub problem is that smaller array starting from like over here at this index, and that will return this destination pointer. So for our main problem, we want to return this pointer -1, right? So that's why over here we have this like -1 that's tacked on to our return value. So it's okay if you don't understand this pseudocode. It's not like the main point. The main idea is converting it to RISC-V, right? So try converting this pseudocode to RISC-V. I'll give you until the end of the review session, and then let's go over it. Right? I'll stay for a bit afterwards. Okay. So converting this pseudocode to RISC-V, and remember calling convention. Right? Khalid? It was supposed to be like an hour and a half long, but I think I can get away with 2 hours because we booked this room for 2 hours. So max 2 hours. Yeah. And for the people on Zoom, you can use Ed to ask questions. And the post is linked up there. I'll post that again. Yeah, add this link. Okay, so we'll get back together at 3:30. quick question? Yeah. Load address. I think, if I remember correctly, load address takes a label. Oh, okay. So for reference, load address, I'm pretty sure it takes a label and then returns some value based on the label. I think the instruction that you're referring to is probably a load word or load byte, some sort of instruction like that. So in that case, you would usually use that at the top and bottom of your function. So like at the top, you do like store word, right? And then put in some byte offset. So let's say you want to store one value, you would decrement SP by 4, right? And then store at SP with a 0 offset, right? Does that answer your question? Yeah, okay, cool. Okay, so let's talk about this. Our recursive solution. This one's more challenging than the previous one. And you also have to be aware of calling convention, right? So let's go over this like solution that doesn't involve calling convention, and then we'll insert the calling convention at the end. Right? Oh. Okay. So yeah, if n is equal to 0, remember a2 is n. If n is equal to 0, you can end your function. Right? If not, then you read the source array and copy it to destination, right? And then if that source character is 0, then you return the destination value, right? Destination array. So if S0 is equal to 0, if the character is equal to 0, you just end, right? Okay. And then if not, let's set up our recursive call, right? So we're recursively calling stir and copy, right? And we need to load our arguments first, right? Before you call a function, load things into the A registers. So inside A0, let's put, okay, so we're changing A0 to add 1 to the destination pointer. We are adding 1 to our source pointer, right? And you can refer to the recursive call in the pseudocode. So we're adding 1 to our source pointer, and then we're decrementing n, right? We call our function now that we loaded our arguments, and we can find the return value in A0, right? The return argument for our recursive call is in A0, right? And we want to return 1 minus that value. So let's just subtract 1, and we can return, right? A0 is already the destination pointer, right? So we can return. Any questions on this before we insert the calling convention stuff? No questions? Okay, cool. So yeah, there's a problem here, which is we're using S0, but we're not saving the original value, right? We're using S0, register S0, and we're also calling another function, right? We're recursively calling stir and copy. Right? So we need to save these values, save RA and save the S register, right? What is this? Okay, yeah. So this is our fixed recursive solution that includes calling convention, right? So our code is the same as before, but we put some space for calling convention, right? So what do we need to store? We need to store 2 things. What do we need to store? Exactly, RA and S0. And why do we need to store both of them? Uh-huh. Yeah. Yeah. Exactly. Yeah. So the answer was by calling convention, we have to save the S register value. And we are also calling another function, so we have to save RA, right? Okay, so we decrement our stack pointer by 8, and then we store these values, RA and S0. Question? Yeah. So that's a good question, and I can't be certain that it would work. I do think that it looks like it would work because after our recursive call, we don't use the T register at all, right? Like after jump and link, stir and copy, we don't even use the T register. But I'm tempted to say that it would be fine, but of course I can't be certain without just like running the code and seeing if it works, right? Someone on Zoom raise their hand. Lin Jung. You can unmute.
Hi. So I have a question.
If you're talking,
can I
then
have a question?
unfortunately I
Just a
can't
question
hear you.
then. Okay.
Let me check chat. Okay, there's a question. Shouldn't we put the prologue outside of the function? Shouldn't we put the prologue outside of the function? So, okay. So I guess my volume has some issue. Yeah, I was surprised that everything was going so smoothly. There's always some Zoom issue. I think my volume is on. Yeah, my volume is on. Maybe I have to change an audio setting. Select a speaker. Maybe, okay, I'll just play it on my MacBook. Okay. Can you try talking again?
Hello.
Oh, hi, I can hear you.
Okay. I have a quick question. So why is load byte and store byte? Why not load word and store word? Since the address should be integer, right?
Okay. So the
Yeah.
question was, the question from Zoom, thanks for the question. The question was, why are we using load byte and store byte? Why can't we use load word and store word, right? That's a good question. The reason for this is because, like I mentioned before, this function takes in character arrays, right? They're still characters. And the size of a character is 1 byte. So if you want to read a byte or store a byte, read a character or store a character, then you would use load byte and store byte, right? The case where you would use store word and load word is if you're working with integers or if you're working with memory addresses, right? So yeah, that was a good question. Jason Zhao, go ahead.
Yeah, so I was wondering, like, why are we saving RA? Because I think shouldn't RA be like the same throughout any depths of recursion?
Okay, so Jason's question was, why are we saving RA? Why do we need to save RA, right? So the reason that we save RA, so you can imagine that stir and copy was called by some program, right? And when they called stir and copy, they would say Zhao stir and copy, right? And that sets RA to be a return address to go back, right? So now at the end, so like within stir and copy, we know RA has our return address to our original program, right? Within stir and copy, right? So when we're calling within stir and copy, we're calling another function. We're calling stir another like iteration or another like recurse of stir and copy. And when we call that Zhao stir and copy at the end, when we call that, it will overwrite our original RA value, right? So that's why we store RA, is because we need to remember our way back, right? Without having our like memory overwritten by another function, right? So that's why we store RA. There's a question from Yu Wei.
Yes, I want to ask about why we are checking like two ending condition. The first one is n equals 0. The second one is checking whether source is reaching a null denominator. Because I'm thinking if the n is correct, then n equals 0 is sufficient to stop the recursive call, right?
Okay, good question. So the question was, why do we have to check two conditions? We have two branch conditions, right? There's one that's branch if equal a2 x0, right? Where a2 is our destination, right? Or sorry, a2 is n, right? So we're checking if n is equal to 0. So that's our first condition, our first check is n equal to 0. And why do we also have to check our source, the character? Why do we have to check if it's a null terminator? Right? Okay, so that's a good question. The reason that is it's just like part of our function behavior, right? That's just the definition that was given for stir and copy. And that's the only reason we're doing this in our code. The larger reason is if a programmer puts some n, so the main idea of this function is we're copying characters from a source array to a destination array, right? Let's say our source array is only 3 characters long, right? Right, 3 characters long. And the last character would be a null terminator, right? So, but let's say a programmer puts in copy from that 3-letter array, right? 3-letter string. I want you to copy 5 characters from that, right? So you were right, where if the programmer puts in a proper, correct, valid value for n, then there's no need to check for the null terminator. But if they don't put in the correct value for n, then we need to be sure that we don't like read the garbage values past the null terminator, right? Because the null terminator tells us where the end of our string is. So if we copy like more characters than the string has, then we're just reading garbage values at the end, right? So good question. Okay. So yeah, that's our solution. Calling convention. Okay. Jason, do you have a question or is your hand?
Yeah. I mean, like, thank you so much for your answer, but like, I'm still like wondering, like, in this case specifically, for RA, if we do not save it, does it still work? Because like it's after the line gal string copy, right? So it's still like the same line. So like, what if we don't save it? Does it like return to the same address like every single time, like every recursion? Or do we like have to save it? Otherwise the program will just error.
Okay, so good question. So Jason's question was, why do we have to store RA if we're just like looping to the same function, right? Because stir and copy, theoretically, the return address and the address that we're jumping to are like the same thing, right? So why do we have to store RA if we're just looping to the same function, right? So the reason for this is we're not just storing a return address to stir and copy. We're not just storing a return address to stir and copy, right? When some other program calls this function, it will be in like potentially some other location in code, some unrelated program, right? And then when they call JAL stir and copy, it's storing the RA of that point in the program's code, right? So that's why it's necessary to store RA, right? Before we recurse. Hopefully that answered your question. Yeah, no problem. Okay, so quickly, I think we are running out of time. Let's just go over instruction formats super quickly. I think one example problem's good enough because once you know how to do one, you can use the same like method to solve the rest. So let's go over instruction formats. Okay, so let's convert 32-bit binary to RISC-V, right? So I'll give you guys just like a couple minutes, or actually, let me get a raise of hands. How many of you want to try this problem right now? Okay. Okay. So how many of you want to just like go over the solution together? 1, 2, 3, 4. Okay, so it was a close call, 4 versus 3. So let's just go over the solution. And I think that is better for the sake of time because we did go over already, right? Okay, so let's convert this. What's the first step? Can anyone tell me the first step we should take? Yeah, sure. Hey, let's convert to binary. Right, so now we have our binary. What's the next step? What do you do? Yeah, exactly. And how long is the opcode? Right, okay. So we need to identify the opcode to tell us what kind of instruction is it, right? Because if we don't know what type it is, we won't know the format, right? So let's get our opcode. The opcode is always the furthest right 7 bits. Okay, that's our opcode. And in practice, when you're taking the exam, you would just check your reference card and then find the opcode and say, okay, that's a B-type instruction. But for the sake of the answer, I'll just give you, it's a B-type instruction, okay? Okay, here's a format of a B-type instruction from our reference card, right? So, and these are the amount of bits that they are. So now we just like select the bits that align with our format, right? So we're just reading this binary and taking out the bits, right? And now we can read off using our format the information for our instruction, right? So our func3 is 0, right? 0, 0, 0. And we can check inside our RISC reference card that it's branch type instruction. And the instruction is specifically branch if equal, right? So that's our instruction. We know the instruction. RS1 is 0, 1, 0, 1, 0. And that's X10. And X10, you would check the card and you look and say, okay, it's A0, right? RS2 is just 0, so it's X0. And our immediate. So this one is sort of tricky. And I purposefully made it a branch type instruction. So a common mistake is forgetting to shift your branch, your immediate, for a branch type instruction, right? So see at the bottom, or hopefully you can see it. At the bottom, we read off the instruction, getting our 12th bit, then our 11th bit, then 10 through 5, then 4 through 1, and you just put them next to each other, right? So let's say we read it, right? And we would get some value. It's a bunch of ones and then 2 zeros at the end, right? So we read our immediates in signed representation, 2's complement, right? So a bunch of zeros and then a bunch of ones and then 2 zeros at the end. What number would that be in 2's complement? A bunch of ones and then 2 zeros at the end. Yeah. Yeah, it would be -4. So you have a bunch of ones, 2 zeros. You flip the bits and add 1, right? So then you have a bunch of zeros and 2 ones, and then you add 1, and then you get 0, 0, 1, right? So 0, 0, 1 is -4, right? Because we knew it was negative from the beginning, right? So hopefully that makes sense. But if you put -4 on the exam, then it would be wrong, right? Because you have to shift our immediate to the left, right? For B-type instructions, you have to shift the immediate to the left because we don't encode that rightmost bit inside our like 32-bit instruction, right? We don't encode it. So remember to like take your number and shift it 1 over, right? So then our -4 would just be multiplied by 2, right? And you get -8. So that's their answer. The answer is break if equal to a0, x0, and -8. Okay. So that is the end of the review session for RISC-V. If you have any final questions, feel free to ask. I will be up here for a bit after the session if you have any questions. And if not, here is a link for a feedback form, or you can use the QR code and just scan it. Okay. Thank you. Good luck. Oh, and also there are 3 other review sessions that are coming up. So check ed. There will be, I think, RISC-V is covered today. I'll also cover C and like memory. And I think Rohit is covering Boolean logic and finite state machines. And then there's one more. I try to remember what it was. Oh, number rep. Yeah, number rep. Yeah. Question? I recorded mine. That's for certain. I'm pretty sure the rest will also be recorded. Yeah. One slide. Like this. I guess I'll stop recording now. Thank you guys for coming, the people on Zoom. If you have any questions, make sure to post on Ed. If not, I'll end the recording and you're free to leave. From Piyush, I'll take your question.
Yes, hello. Can you hear me correctly?
Yeah, I can hear you.
Also, could you go back